Hello class, welcome to the next section, chapter 4.2. Today we're going to talk about derivatives of the next type of function, which is exponential functions. These are not typically as easy as polynomials, but they're still pretty easy to deal with. For this section, since we don't have all the tools available yet that we need to develop, we're going to kind of go in a roundabout way to solve some of the more difficult exponential functions. So really what we're going to do is we're going to use a lot of the rules of exponents in order to simplify these things. So for our derivatives of exponential functions, let's say we have some base to a power where the input is the power. This can be any base, it could be 1, 1/2, it could be e, any of those things. The derivative of this function, we're not going to develop it the same way we did for the polynomials because we don't really have the skills necessary yet to do that. So we're going to just go ahead and give you the formula, right? So the formula is the natural log of the base times our original function. Okay, so if this was like 3 to the x, for instance, the derivative would be natural log of 3 times 3 to the x. So we keep the same function, but we just take the natural log of whatever that base is. Note that if we have y equals e to the x as the function, then when we take its derivative, we'll end up with the natural log of e times e to the x here from following this formula. And we should know that the natural log of e is just 1, which means that I end up with just my regular function, which is really nice. Makes things really easy. So if I have e to the x, the derivative of e to the x is just e to the x. Okay. Now this changes once we start manipulating this a little bit and adding some things in here. So that's when we start to use the rules of exponents, which is what we're going to cover in this video. So we're going to do a couple of examples. This video is going to be really short. We have, I think, 3 examples and then that's it. We don't have anything else to talk about here. We could do tangent lines and all that kind of stuff, but we've done that a lot. So really we're just going to focus on how to find the derivatives at this point, right? So let's say that we have a function of pi to the x plus x to the pi, right? And we want to find the derivative here. So first and foremost, we have to understand that these are not 2 exponential functions. We have one exponential function that has a base of pi, and then we have a power function, right? A polynomial, because its base is x, and it's x being raised to the pi power, right? So I know they look similar, but it's important to understand which one's an exponential function and which one is a power function. So when we take the derivative, this first term we'll use our new rule for, and the second term we'll use the rule from the previous section for polynomials. So the derivative here is going to be, using this rule, I'm going to take natural log of my base, so natural log of pi, times the original function, which is pi to the x. The second term, which is a power function, is going to have its exponent drop down to be pi, and then the exponent of pi here is going to reduce by 1. So this will turn into pi x to the power of pi minus 1. And that's it. We can't simplify any further than that. Okay. For our second example, we're going to have 2 to the 5x. So here we want to use our rules of exponents to make this simpler, because if you notice, the 5 is attached to the x, but we don't have a rule for that. Okay, we can't just make stuff up. So we don't have a rule for when this happens. So what we're going to do is we're going to use our exponential rules. So I know that when I have in the exponent position 2 things being multiplied times each other, that's because I'm raising a power to a power. Okay, so I can take my derivative of 2 to the 5x and I can separate that using my rules of exponents to try to make it easier. So it's like I have 2 to the 5th raised to the x power. Okay, 2 to the 5th I know is 32. So this can be rewritten as 32 to the x power. So instead of having it as 2 to the 5x, I use rules of exponents and I rewrite it as 32 to the power of x. So now that it's in the form that I want, that I'm familiar with, I can take its derivative. So the derivative of this is going to be the natural log of 32 times times 32 to the x. Okay. Now if you left it here as an answer, I'd be somewhat okay with it, but this can be simplified further, right? We know that this is 2 to the 5th, so I can rewrite this as natural log 2 to the 5th power. My rules of exponents say I could pull out that 5. So this is really 5 natural log of 2 times 32 to the power of x. So this would be its fully simplified form. So don't forget to simplify things all the way. Do not give me a decimal form for your answer for natural log of 2. A decimal form is an approximation. We want to use exact values. So if you give me in a decimal form here, that's not exactly natural log of 2. That'll be some approximation of natural log of 2. So why use an approximation if you have the exact value, right? So keep everything in exact values in this class as much as possible unless stated otherwise. So we have one more example. We want to find y prime for y equals e to the 3x plus 1. So same thing, I want to simplify this by using my rules of exponents. So I want to apply as many rules as I can. So again, my goal is to get it to look like this. Okay, I want to get it to be a base to a power. If I can get it to be just a single base to a power, then I can take its natural log. When I have a base to a power and a bunch of stuff going on in the power, that's difficult for me to deal with at this point. So my goal is to isolate it so I have one base to one power, and then anything else that's going on, I should be able to separate out. So let's take what we have here. You see I only have one x, so I should be able to separate and have only one e to the x present, and then a bunch of other things going on based on my rules of exponents. But I want to try to separate just that e to the x if I can. So let's rewrite this in terms of powers. So I know that when I have addition, that means that I'm multiplying one of my base to a power times another of those bases to a power, right? If I have x cubed times x cubed, I get to add those two cubes together, right? So that turns into 2, or x to the 2 times 3, right? Because there's 2 of them. So here I can separate this out. So that's the first thing that I want to do is separate that into 2 pieces and then separate those 2 pieces into 3 pieces. So what do I mean by that? E to the 3x plus 1 can be written as e to the 3x times e, and then that e to the 3x I can separate to look like e cubed to the x power. Okay, so I kind of did 2 steps here because I am really just doing what I did here before, where we had 2 to the 5x, and I rewrote it as 2/5 to the x. Okay, so I'm doing that coupled along with another step of moving this e. So if I were to combine this to be one base, you should notice that it would be the same thing, e to the 3x plus 1. So this extra e out here being multiplied is where this plus 1 comes from, and this e cubed raised to the x is this e to the 3x. So it's all with the same base, and then I'm just separating its powers of exponents. So now if you notice, I have it in the form. I do have an extra e here, but e is just a constant, okay? The x is what the variable is. So this is just a constant multiple of e to the 3 to the x power. So when I do my natural log, I really just focus on that first part because remember rules of derivatives saying I can just kind of pull this constant out and apply it later. So I know that my derivative is going to be the natural log of e3 times e3 to the x, okay, and then times this constant that just kind of gets brought along with the whole thing, right? So from here I want to simplify as much as possible. I know natural log of e to the 3 is just a 3, and then I have this e, so the constant term is 3e, 3 and e, and then I can just finish working this in. So I'll really have 3e times e to the 3x, which means that I can combine that e also and have it as 3x plus 1. Okay, so a lot of rules of exponents going on here. Make sure you go over this yourself a couple of times on your own. Maybe write this out and then take its derivative and then check your work against my work for practice.